Alright, so as we've learned in the last couple of topics, we have this thing called energy transfer. And with energy transfer, we learned a very easy way of calculating that energy transfer. It goes back to the good old F versus delta X graph. We said the area of this graph was that energy being transferred. Now what we are going to do is we're going to hopefully discuss a vocabulary word that is going to do that. And then what's going to be nice is we're going to see how that is going to affect LOL diagrams. There's a lot of different interesting aspects that we have not explored with LOL diagrams, and it's based upon system. So you'll see the whole goal of this lecture is choosing your system the right way. And based upon that and based upon the things that we know from the last couple of ones, we are going to sum that all up into being able to calculate energy transfer, calculate forces, calculate all of these different things, and it's all going to be really delving around proper system selection and other things like that. So to begin, I think the easiest way is to look at an example. So the example that we are going to take a look at here is a spring that is sitting on the ground with an object on it, and then that spring releases it, causing the object to fly up and get to its max height. So the moment we look at this example, we have done a problem very similar to this in class, so this should be kind of easy to wrap your head around, because we have drawn an LOL diagram. And the LOL diagram we are most common with looking at for this example is you can say at the beginning, as long as we choose our system as the ball and the spring and the earth, at the beginning we can say that that ball has ES, or I'm sorry, the ball, spring, earth system has ES stored into it. And as long as we make our zero height at the ball at that moment, what we could do is we could say then all of that energy has been transferred into EG. At this moment, we are used to energy conservation, and you'll notice that there is no other case for this. All of our energy balances, total energy here equals total energy on over here. So that's a very nice, interesting, simple case, and we've said there's a really nice, easy ES to EG calculation that you can do. Now, the way that this can be a little bit different is if we were to choose our system so that maybe we do not include the spring. So if we just did the ball and earth system, if we were to do this, you're going to notice that the LOL diagram changes. You'll notice that energy conservation in this system does not happen. So at the beginning, we can say that we have no ES because the spring is not in our system, so it is not storing any energy, and there's no other energies. EG, because we're still at zero, we don't have anything there. EK, it's not moving while it's on the spring, so we have no energy in the ball earth system. And then, sure enough, energy does appear in our system, and you'll see that then our EG appears. So how do we represent this? How do we do this? What we do is we draw an arrow saying energy has come into our system, and we label that W. W stands for work, and work by definition is just an energy transfer by a force. And usually you'll say it as an outside force. Outside force acting upon the system. So you see that this is work, and we want to be a little bit more specific, and we want to say the object is the spring. So what's really kind of fun and interesting when we look at this example is we can go into and just kind of notice that in our first example with the spring in our system, there is no outside force. But the moment we look at this diagram and we notice that the spring is outside the system, the spring will be doing work on our system or causing energy transfer. And this is work going into our system. The other case that we can actually look at for this is looking at an LOL diagram where now we can have the ball in the spring as our system. However, we can then take out the Earth. So, in order to do that, let us first figure out what's going on here. Let us move over, and let's draw an LOL diagram for now the ball spring system. So we've kind of changed our system a little bit differently now, where now at the beginning we do have that ES that was originally there. However, because the Earth is not in our system, you'll notice that the EG will be absent. There will be 0 EG and no ES and no EK. So all of these things have 0 energy stored into it at that moment, and you'll notice that the energy originally that's here now leaves our system, and we again will call that work. This is work again by Earth, and this is a different type of work. Some physics teachers will refer to this as negative work. I don't like that idea. I'd rather refer to this as just energy leaving the system, or work being done on our system where it is again losing that energy, or an energy transfer outside of our system. And you can see that that W comes into play there. And once you start realizing some easy calculations, you start to notice the amount that you lose. The amount right here, this W, is just going to be the difference in energy from your first bar diagram to your second. So you can look at the total here, total E, and the total energy here. And you can say, oh, the difference in those energies is going to be equal to the work. So you can start to do easy calculations once we know how to calculate these bars, and you can start calculating that. Now, why is this important? Why is this something that we want to consider? Why do we really want to do anything like this? Well, the goal now is to say, if I do have an outside force acting on my system, how can I understand what's going on? So I understand what vocabulary is going to be work, so make sure you make that connection there. I know how energy transfer is represented in an LOL diagram, we got that down. And I know how to calculate this energy transfer in 2 different ways. That is the big piece that we are looking at. So this is one way to do it, just looking at the energy change between one diagram to the other. You can almost just say, if this was 40 joules and you have 0 joules on over here, what is going to be the work? The work is going to be 40 joules because that energy has left. So that's a very easy way of doing that. However, there is that second way of doing that. Let's say we knew the force that was going to. So the moment we talk about work or an energy transfer, we think about, oh, an energy transfer, what graph do I always go to if I want to calculate an energy transfer by a force? Well, sure enough, we go back into the last few lessons that we've been doing, and we go back to that F versus delta X graph. You can always go here, and you can say that this area is actually equal to the work by that. So, in order to choose your system properly, one of the biggest aspects is if a force is given to you. If this is given to you, it says there's a constant force, or there's a force that's acting on the system, go calculate it. What you want to do is you want to make that force the outside. So, if you have a situation where you are trying to link forces with energy, the way to do this is the way of work. And the easiest way to break down a problem like this is you want to be a smart system selector. So a smart system selector will be able to choose the correct system so that this force right here will be on the outside. And in order to do that, there's a very easy way to say then how much work is. Then of course we can take that work and we can say the work is going to be the area of that F versus delta X graph. So to give you a quick example, if we looked at this person pushing this box, and we want to know the force that he would have to push it to move it, let's say 5 meters. And we know that after those 5 meters, the velocity of the box gets to, let's say, 5 meters per second, or just some velocity, and it has some mass m. The way that we would want to do this is I want to be a smart system, and I want to think about my system as being everything but the force that is being caused, the force that I'm looking for. So I would say the box, and this would actually have to happen on a frictionless environment, or maybe not. Anyways, it really doesn't matter as long as when I draw my LOL diagram, you'll notice that there is no EK, there is no EG, there is no ES, because all what I have is box, and let's put friction in there just for kicks. Box in the floor, so we have both of that. And because I've chosen my system like this, why is this so nice? Because when I get EK at some point, EG, ES, and then of course the E internal that also appears there, what I can do is I can realize that the work done by the person is actually going to be equal to both that of the EK plus E internal. And the way that I can discover this, it's really simple. It's because I made sure that my system made that happen. If I would have put the person in here, you would have had this weird E-chem on over here that would have been present, and then you don't necessarily see that the work by the person is being directly affected by the E-chem. So because I've made this choice, you'll see that I could get this, the work is equal to EK and E internal, and then I go back to my final idea that would say that the force sitting on over here over delta X, I know that the force the person applied, and looking at this, I would say, oh, this work here, the energy that I just calculated, is that area of that graph, and if I knew this was 5 meters, I can go and I can actually easily calculate what this value would have to be based upon that. So that's a very, very, very quick way in understanding how work is associated and connected to forces.